Amber, our director, sir, is going to join within a couple of minutes, and we will start the program.
Okay.
Okay, sir.
No, uh, Rishika, now we can start the program, please.
Good evening to each one of you present today. It is a moment of extreme pleasure to welcome the guests who are present here to attend this session. On behalf of the IEEE student branch of Shri Ram Swaroop Memorial Group of Professional College, Lucknow, I offer my regards to all the dignitaries and the people joining us. I convey my regards to the chief guest of the day, Sir John D. MacDonald, sir. Thank you so much, sir, for accepting our invitation and coming over for the session. We also welcome our honorable guest of honor, Professor Ashish Kumar, sir, respected AD Engineering, and Dr. Indhu Prabha Singh, ma'am, respected HOD of EE and EN Department, Dr. Khadim Moin Siddiqui, sir, respected Engineer Sandhya Srivastav, ma'am, erudite faculty members, and all the attendees. The scheduled session will focus on the purpose of IEEE Power and Energy Society, and that is to provide the world's largest forum for sharing the latest in technological development in the electric power industry. We serve our vision as to generate innovative energy solutions for the betterment of society and to emerge as a leading community for technological and scientific knowledge and skills. Our mission is to influence notions and interests of students for innovative thinking and to foster professional competence for a better future. Now, I would humbly like to request our Women in Engineering Branch Advisor, Engineer Sandhya Srivastav ma'am, to address the audience with her warm welcome note for the commencement of the event. Ma'am, please.
Thank you, Rishika. On the behalf of entire IEEE SRMCEM Power and Energy Society, it gives me immense pleasure to welcome our honorable speaker, a dynamic person and a great personality, Sir John D. McDonnell. He was PE Smart Grid Business Development Leader, GE Grid Solutions, and past president, IEEE Power and Energy Society. IEEE PES focused on the scientific and engineering knowledge about electric power and energy. And presently, I think 38,000 plus members in the society. When I go through Sir John's profile, it's a very impressive, I must say. And in Sir's profile, he teaches a smart grid subject, and present session, I also teaches the same subject. On this inaugural ceremony of Power and Engineering Society, we are honored to have you, sir. On this platform, we look forward and we are very excited for the session. And I also welcome honorable guest of honor, Professor Dr. Ashish Kumar Singh, sir. Sir has served as chair of IEEE UP section for 2 years. Sir, your handholding and guidance always motivate us. And I also welcome our honorable director and advisor, IEEE Power and Engineering Society, SRMCEM, Dr. Bhavesh Kumar Chauhan, sir. Sir, your presence always needed and motivate us. And I welcome all the erudite faculty members, all the my dear students, and definitely look forward this inaugural ceremony of Power and Engineering SRMCEM IEEE branch. Thank you so much everyone for joining us and look forward this session. Over to you, Rishika. Thank you very much.
Thank you so much, ma'am, for your kind words. Here now is Amber Mishra, sir, Chair of IEEE Student Branch SRMCEM, Lucknow, to enlighten us with his words. Sir, please.
Good evening to one and all. I'm Amber Mishra, serving as the chair of IEEE Student Branch of Sri Ram Sarup Memorial College of Engineering and Management, Lucknow. On this auspicious day of the inauguration ceremony of Power and Energy Student Branch Chapter, I warmly welcome all the dignitaries and participants with a vision of becoming a crucial organization of students for technological development and fostering a community in college well equipped with technological and humanitarian skills. The student branch of SRMCM has immensely grown over the past few months, and I congratulate all of you as we inch close to 400 active IEEE student volunteers in our organizational unit. Now, we introduce to you the very vibrant and energetic office bearers of Power and Energy Society Student Chapter. Over to you, Ayush.
Hello everyone, I am Ayush Pandey, serving as the chair of Power and Energy Society chapter of SRMCEM, Lucknow. This chapter will facilitate collaborative learning among members and will promote the study and practice of power system engineering. Thank you.
Hello everyone. Hello everyone. My name is Anant Verma and I am serving as Vice Chairman in IEEE Power and Energy Society as a student chapter. It is a matter of great pride to serve in this prestigious community and hopefully we inspire and contribute towards the society. Thank you.
Good evening, everyone. I am Rishika Pandey as Secretary of IEEE Power and Energy Society, chapter of SRMCEM. Thank you.
Hello everyone, I Abhishek Singh, serving as Treasurer in IEEE Power and Energy Society SRMCEM Lucknow. I am a second year student in Electrical Engineering Department. Thank you.
Hello everyone, I am Harshit Jaiswal and I am the web designer of the Power and Energy Society chapter of SRMCEM, and it is a great honor of pride to serve in this society. Thank you.
Now, I would like to invite our guest of honor, Professor Ashish Kumar Singh, sir. Sir has served as a chair of IEEE Uttar Pradesh section for 2 terms. Sir is professor in Electrical Engineering Department at Motilal Nehru National Institute of Technology, Prayagraj. So please enlighten us with your words.
Thank you very much for inviting me to this occasion. And I'm really very happy to know that you are going to add one more feather in your cap of IEEE activities in your institution. And this all has been possible with the continuous support of the young IEEE volunteers of the institution. And specifically, I will like to mention Dr. Khadim and Professor Chauhan for their support to the institute and IEEE volunteers. I'm thankful to our chief guest also for giving their precious time for this activity and for the motivation of our young volunteers. And I'm really happy. I'm happy to see that the growth which they have shown and the participation they have shown in last few years in IEEE student branch activities, that is really wonderful and motivation for others IEEE volunteers. Thank you very much for being with us in Uttar Pradesh section. Thank you.
Thank you so much, sir, for your kind words. Now, we request our honorable chief guest, Sir John D. MacDonald, PE. Sir, Sir is a smart grid development leader for GE Grid Solutions business. Sir is past president of the IEEE Power and Energy Society Finance Committee, chair of the Smart Energy Consumer Collaborative Board, and past chair of IEEE PES Substation Committee. He was on the IEEE Board of Director as the IEEE Division 7th Director. So please enlighten us with your words of true wisdom.
What an exciting time. And I'm really happy to be a part of this inauguration. I really am excited whenever I see a new chapter being formed. Okay. And and the reason is it's a tremendous opportunity for all of you to advance your careers, right? To develop your careers. And you know, I'm an IEEE Life Fellow, and this is my 51st year of IEEE membership. So I've been an IEEE member now over 50 years total. And I would say that because IEEE is a volunteer organization, there's no limit to you in terms of what you can do. Okay? In other words, the only limit to you is you yourself by not taking advantage of all the opportunities that IEEE can offer you. Okay? And there's three primary areas that, as an IEEE PES chapter member, there's 3 things that you want to focus on. And these are the 3 things in 51 years, these are the 3 things that I've focused on to help me in my career. One is learning the technology to a much deeper level, okay? IEEE provides you opportunities with courses, with technical tours, papers. I've co-authored 5 books. I've published over 150 papers and articles. There's tremendous resources available to learn the technology much deeper. Second is you want to expand your network, okay, of industry contacts and industry friends. I've been working 48 years now full-time in power system automation, and I've had 6 different jobs in 48 years, and every one of those job changes was through a friend in my network, okay? Every one was through a friend in my network. My friend, the reason I'm at GE now, I was very happy with my previous job, and a friend said, "Hey, John, there's a tremendous executive level opportunity at GE that's perfect for you." Okay. And I said, well, I'm happy doing what I'm doing. And he said, no, you need to do this. You need to interview. And it was through my friend that I ended up changing jobs. Okay. So expand your network of industry contacts. Okay. And one thing that's very important with this is LinkedIn. You want to have a profile on LinkedIn, and you want to keep your profile very detailed and up to date. That's how many companies find candidates for good jobs is keyword searching profiles on LinkedIn. Okay. And then the third thing is leadership opportunities. IEEE is a volunteer organization. We welcome people to volunteer for any kind of leadership position. Okay. So again, the only limit is yourself. Don't limit yourself. Take advantage of as many opportunities. I've had many leadership positions in IEEE. Right now I'm on the IEEE Foundation Board of Directors, and I'm chairing the committee to celebrate the 50th anniversary of the IEEE Foundation, which will be next year. And I've built a team of people. So, you know, I'm 70 years old, 51 years now with IEEE, but I'm not stopping. Okay. I'm very excited, and I continue to want to participate in IEEE because of all the benefits. Okay. Now, the success of a chapter is based on its leadership. So I see some very motivated, very excited leaders that I've just heard. And it's up to you then to be very active, right? Interest other people, expand your membership, and provide value to all your members. That's what's important. Members, you'll grow your membership and you'll retain your members if you provide value to each of them. So you want to have programs, create opportunities for growth, and provide value to everybody. And let me finish by saying, if I can ever help you with your strategy, with your programs, I've been a distinguished lecturer for IEEE PES since 1999. I give many distinguished lectures every year. If I can ever help you in any way, please contact me. I'd be happy to help you with your chapter. Okay. So let me should I go into my talk now, or what should we do? What is next?
Honorable sir, we can start the presentation because
Okay.
yes, sir.
Well then, I'll share my screen. Okay.
Sir, we have given you permission that you can share your screen, and if you are unable to share, then please inform me.
Yeah. And you know, I don't want this to be a lecture. I'd really like to have an interactive discussion.
Yes, sir. Yes, sir. We are waiting for an interactive discussion.
Can you see my slide?
Yes, sir. It is visible. Yes, sir.
Okay. So these are some of the positions that I've had in IEEE. Okay. And again, volunteer for as many positions as you can, and work very hard to be a good leader. All right. Now, this is some other things about my background. And one of the things that's very important to me as I've gotten older is to take good care of myself with health. okay? And so you can see that, you know, what's important to me is to eat healthy, exercise on a regular basis. And I have a trainer in the lower right there who's a professional American football player. And I work out 5 times a week with boot camps and run 5K races at 70 years old. Okay, so I you know, I was always thinking that I can always get another job with work, but I only have one body for my whole life. So my priority should be a higher priority with my health than with my work, right? I can't get another body. So I need to take care of myself. So I changed my priorities about 11, 12 years ago to be much more focused on health. And that's very, very important. The better you are with your health, the more effective your work is. Okay. So I'm gonna highlight some key areas in power systems, and then if you have any questions or comments, you know, I'll make sure we have time to go through those. So first thing is there's some key industry societal trends, and what's important is we have to get involved in organizations like IEEE. You have to know what's happening in the world around you. If you don't get involved in like IEEE and you just do your studies at the university or you just do your work if you're working full time, you're 100% internally focused and you may be making decisions that aren't the best decisions because you don't know what's happening in the world around you, okay? Your decisions may not be the best. Something that's happening in the world, some trend may adversely impact your decision. Okay, so a couple of them are, we've transitioned from devices, microprocessor-based devices and systems, and now we think of a holistic solution. Holistic means company-wide, and a solution is a set of technology components integrated together to successfully interoperate to meet the business needs of the customer. So when I teach at Georgia Tech, I teach at University of Tennessee, I teach at the Wentworth Institute of Technology, I teach graduate and undergraduate electrical engineering courses. We teach the students to always think of the big picture. Don't just think of the microprocessor-based device in the substation, but that device has two-way communications and it could be a node in a bigger network. The holistic solution has much more benefits to the customer than just the device or system itself, okay? Success is technology, standards, and policy, all three, not just technology. Today, technology must be based, based on industry standards because we're taking devices from different vendors and we're connecting them together to be able to talk to each other. And these are made by different companies. And the only way we'll be successful is if each of those companies comply with the same standard or sets of standards. The grid today, we want a self-healing grid, which means that we put logic out on the grid and the logic is always looking for potential problems. And this logic can detect a fault, isolate the fault. First it detects it, then locates it, then isolates it, and then restores service upstream and downstream of the faulted segment, all within a minute or two with no person involved. Okay, that's truly self-healing, and we have that technology today. It's called fault detection, isolation, restoration software application. There's much more focus today on grid resiliency. You know, when we design things for the grid, we focus on redundancy and reliability. But when the grid is stressed, it could be stressed with an extreme weather event, right? We find out how well did we do in our designs? How resilient is the grid? How well did it withstand the stress of the extreme weather event? And then I'll talk a little bit more about big data today. One of the books that I just co-authored is called Big Data Application in Power Systems. All right, so there's a lot of focus today on data science, big data analytics, and also making decisions based on data, being a data-driven organization. And then we need to bring together the information technology and operations technology groups within an organization to support enterprise data management. That's IT and OT, operations and IT, okay? So to be able to make sure we can share the valuable information that we have in the field, right, with all the stakeholder groups in an organization, we need to make sure that IT and OT, these two groups, work together, and so that we have very valuable information on the operations side that we can bring over to the IT side, the corporate side, so that all these groups can share the information. They can get the information they need to provide more value to their company, okay? Now, I like to call this the smarter grid rather than smart grid. Smarter, because what I show here shaded in light gray is the intelligence we've been adding to the grid for many, many years. Okay, you know, I started working, I finished graduate school in electrical engineering in 1974 and began working and adding intelligence to the grid a long time ago. And that's what we've been doing previously is in light gray. But what's in light green is what we're doing new. And that's the smarter grid, okay? For instance, on the bottom there, voltage control. Voltage is directly proportional to load. So if it's a summer peaking utility and it's a hot summer day and utility is approaching its previous peak, we will lower the secondary voltage, which will lower the load, okay? Now, we also do reactive power control, right? We want to reduce the losses on the system. We call that VAR control, right? Reactive power control. And we've done that separately for a long, long time to improve the power factor on the grid. The difference today, that's the light gray part. See, it's shaded halfway here on the bottom. The light green part of this is today we're integrating voltage control and reactive power control. We call it integrated volt-VAR control or volt-VAR optimization, okay? We're integrating many more distributed generation, renewable generation into the grid. In the middle, you can see sensors is shaded halfway. We've been adding instrumentation to the grid for a long time, but today what's exciting is we have specialized sensors we can add to the grid. This sensor I'm showing here, I would take the oil from the main tank of the transformer and put that oil through this sensor. And the sensor can detect different gases that are dissolved in that oil. And there's different failure modes that can occur in a transformer that generate a specific gas, like ethane, acetylene, methane. And if I detect the gas dissolved in the oil, like ethane, I know exactly the failure mode that's occurring in the transformer and the rate at which it's occurring. This is very valuable information, okay? So we have a lot of specialized sensors today. We also, next to that, distribution management, I'm going to talk more about this. The distribution system, we designed it for electricity flowing in one direction only, from source down to load. But as we integrate distributed generation, we now have electricity flowing in two directions, right? And so the distribution system is much more complex today. And because of that, we need a separate distribution management system to manage the complexity. We've always had a system for generation transmission. That's called an EMS, Energy Management System. And these are called SCADA systems, Supervisory Control and Data Acquisition. Another one of my 5 books is a book called Power Systems SCADA and Smart Grids. I co-authored with Professor Minnie Thomas. Minnie is at Jamia Millia Islamia University in New Delhi. And Minnie just finished a 5-year assignment as the director of the NIT in Trichy, okay? So Minnie is a close friend. I met Minnie for the first time when I taught a 2-day course in New Delhi in 2003. And I've made, 6 different trips now to India, teaching courses and giving talks and conducting workshops, okay, since 2003. Next is distribution automation. That's downstream of the substation, adding logic on the feeders. We'll talk more about that. and it will also talk about smart meters. So, you know, I mentioned holistic solution, company-wide, and technology components, right? All put together. So I'm going to talk about 6 solutions here. And then on the next slide after this, I'll show you, I'll show you the roadmap, the technology roadmap. So here at a high level, we have asset optimization. So what's another exciting thing is instead of waiting for something to fail, which we call reactive maintenance, now we're getting health information from the asset and predicting with analytics that a failure may occur, okay? And we want to prevent the failure from occurring, not wait until the failure occurs and then react. So we started with transformers, and now we're working with high voltage and medium voltage circuit breakers. Next is demand optimization. That's aggregated load that we use as a dispatch tool in the control center for generation transmission. Third is smart meters and the two-way communications with the metering. Fourth is distribution optimization. And this is where the most focus is today, and actually the strongest business cases. We're putting a lot of effort into optimizing the distribution system. Fifth is transmission optimization. And here we're getting involved with synchrophasers, right? We have phaser measurement units called PMUs that can give us 40 to 50 samples per second of what's happening on the grid. And with the increased number of samples, we have a much better idea of the details of what's happening on the grid, things like transient stability. And then lastly is workforce and engineering design optimization. Most countries in the world today in the energy industry, like the United States, in the next 5 years in the United States, 40% of the employees and 60% of the executives in the energy industry will retire. So the power and energy field is a tremendous opportunity for young people because there are so many opportunities for work and so many new exciting things to do. But as a student, you're learning the science of engineering, which is anyone can do. It's textbooks, professors, courses, what you're doing as a student. But that's not what gives you the value to a company when you graduate and start working. The value you provide to the company is not the science of engineering, but it's the art of engineering, the application of the science. And you can't read a book and learn the art, okay? You have to spend years with experienced people to learn that art. The art is the application of the science in the real world. And one thing that's very important for students and young professionals is mentoring. How do you accelerate your learning of the art of engineering? Through mentoring. You want to choose at least one mentor, an experienced person who has experience and knowledge in the areas that you want to learn, and you spend time with them as much as you can and just learn from them, okay? That's very, very important. I mentor many, many, many young people today, every day, and actually many students and young people from India, okay? And that's very, very important because that's how you increase your value to a company and increase your value once you graduate to industry, okay? So really, and with IEEE Eta Kappa Nu, which is the electrical engineering honorary, I've been in Eta Kappa Nu for 51 years also. I was inducted into the Electrical Engineering Honor Society as a second-year electrical engineering student. But I just recorded on YouTube for Eta Kappa Nu a 35-minute YouTube video on mentoring. And I really suggest you watch that video. And then after that, the IEEE Power and Energy Society recorded my talk called Key Insights to Career Management. In fact, for IEEE PES Day, just 2 days ago, I gave my talk on key insights to career management for IEEE PES Day. And it's reviewing my 48-year career. And there were 12 key decisions I made that impacted the rest of my career. And I go through each of these in this 1-hour webinar, this talk. And again, that's recorded by the IEEE PES, and it's on the PES Resource Center, available at no cost. Okay, so these are things you can, these are things that are readily available to you to watch and learn from and help with your own career. So if we look at the technology roadmap of each of these solutions, you can see the light blue boxes here. This is for distribution, and you can see all the technology components, and they're all over the enterprise. You know, the upper left is the office or control center, lower left is substation, lower middle is the equipment out on the distribution feeders. All of these need to work together in an integrated or a holistic solution. And that's why they all need to comply with the same standard or sets of standards, okay? And then there's 5 key components that need to be invested in by the electric utility. On the top here, first is smart meters. Second is the two-way metering communications, or AMI, automated metering infrastructure. Third is geographic information system. Fourth is outage management system. And fifth is distribution management system. And integration, there's 2 key words today, integration and interoperability for success. And these are some examples of integration. For instance, smart meters provide us the meter readings, but also we ping certain smart meters to get the voltage, okay? And also, when there's an outage, the smart meter will communicate the outage upstream to the outage management system and say, you know, hey, listen, I just have an outage and this is the time it occurred. Very valuable information to the utility, okay? So, as I said, the distribution, well, we can integrate distributed generation at 3 different levels in the grid: transmission level, distribution level, and end user level. But on the bottom here, what I said before was the distribution system, the controls and protection, we design those for electricity flowing in one direction only. And now, as we integrate distributed generation on the distribution system, we have two-way power flow, okay? And that creates some challenges. One would be open circuit over voltage due to unintentional islanding. Second is protection ratings now that don't match fault currents. When we do a protection study, first we do a short circuit study. You know, we need to know what's the magnitude of the fault currents if a fault occurs, because the protective relays have to have the correct settings. But when we model the grid for a short circuit study, we typically only look at the source side contribution to the fault, not the load side contribution. And as the penetration of distributed generation grows, we have a more significant load side contribution, which needs to be taken into account. But the third point here is very challenging in that the load side contribution due to distributed generation varies because the sun isn't always shining, the wind isn't always blowing, and so the fault currents vary based on the intermittency of the distributed generation, okay? This is a microgrid in a rural village that at GE we did in 2010, around 2010. And it was a rural village in British Columbia, Canada. And you can see this village has industrial and residential load, but in it, you know, it has hydrogen fuel cells, solar generation, and hydro generation. Space generation is diesel, which is very expensive. You know, to bring the diesel fuel to a rural village is expensive. And then when the diesel generators operate, they pollute the environment. So we took a microprocessor-based relay in the upper left, the U90, and we added logic to it to become the microgrid controller. And so every 2 seconds, it's making sure the load is satisfied, but also minimizing the use of the diesel generation and maximizing the use of the hydrogen fuel cells, solar generation, and the hydro generation, okay? And then all those little blue boxes everywhere are high-speed communication devices, so we know exactly what's happening throughout the whole microgrid every 2 seconds. Okay. How do we deal with the intermittency? What if the sun isn't shining and the PV panels, the photovoltaic panels, aren't generating? You still want electricity at your home. So where does that electricity come from? It's not coming from the sun right now. So we need what we call bridging storage, right? We need energy storage to help us, or we need fast start, fast responding thermal generation, which is typically natural gas fired. And so today we do have fast start, fast responding thermal generation to deal with the intermittency of distributed generation. And we also are using a lot of energy storage. Now, the cost of energy storage is still somewhat expensive, you know, and the price point of energy storage, we still need additional research to bring the cost of energy storage down, so it's much more reasonable. All right. One interesting project that I worked on was in California, was a distribution feeder that many of the homeowners connected to that feeder installed photovoltaic panels on the roofs of their homes. And so, you know, the question was, what is the impact of high penetration of rooftop solar photovoltaic panels on the distribution grid? And I wrote this article in Power Electronics magazine, August of 2013, and it's available online. So you could search on the internet, Power Electronics magazine, and my name, and you could find the article. But what happened was, in the substation, there's an online tap changer. And that tap changer, its job is, no matter how the primary voltage fluctuates, it keeps the secondary voltage constant, because you want the voltage at your home to be constant. Otherwise, your light bulbs would be very bright, very dim, very bright, very dim, would change as the voltage, secondary voltage changed. So the tap changer is a mechanical controller, 16 raised positions, 16 lower positions, and a neutral position. And it's changing to keep the secondary voltage constant as the primary voltage fluctuates. So you can see the more volatility that there would be in the primary voltage, the more times the tap changer operates. But the more times it operates, it decreases its life, right? It wears out, it's mechanical. So here's a feeder in California that was feeding very nice homes along the Pacific Ocean. And the tap changer was operating about 5 times, 10 times per day. Then all of a sudden, many of the homeowners on that feeder installed rooftop solar panels. In fact, over 35% of the homes on one feeder had rooftop solar panels. Well, these homes are along the ocean, and in the morning, because of the moisture in the ocean, there's a marine, what we call a marine layer of fog over the homes, blocking the sun's rays. As that fog burned off, all of a sudden, all of these homes began generating at the same time. And the voltage on the feeder, you know, once those homes began generating, spiked, shot up like a rocket, and then began to oscillate, because the clouds would go between the sun and the homes, the rooftops of the homes, and the voltage would oscillate. Okay, this poor tap changer was going crazy, operating very, very frequently to keep the secondary voltage constant, because tremendous increased volatility in the primary voltage. And now this thing was operating 120 to 150 times per day, and its lifetime, expected lifetime, went from 35 years to less than 2 years. Okay, so my point in writing this article was, we need power electronic based tap changers. You know, we can't use mechanical controllers on the future grid. It's just not feasible, because there'll be a higher volatility of voltage and reactive power. Okay. Now, the new SCADA system, right, for distribution, we call it ADMS, Advanced Distribution Management System. In fact, a week from Monday, I will be teaching a full day tutorial on this subject at the IEEE Power and Energy Society Transmission and Distribution Conference in New Orleans. Okay, this tutorial that I teach I'll be teaching live a week from Monday, is online also. The IEEE PES recorded it. It's a full day tutorial. And it's also on the IEEE PES Resource Center, available to anybody, okay? As I said, there's a lot of good information for you to help you in your career that's readily available, all right? Now, this is the centralized model of control. The basic SCADA platform, remember SCADA is supervisor control, remote control, and data acquisition. And then layered on top of the platform are many applications to optimize the operation of the distribution grid, okay? On the left is the geographic information system. That's the reference system for the network model in the ADMS and outage management system. And on the right is the field, the substation and feeder devices. So they send information upstream, what's happening in the field every 2 seconds. And then the applications analyze that and then optimize it and send device control commands back down to the field. So there's 3 different groups of applications on an ADMS. These are the real-time applications running all the time that the operators use, again, to monitor and control the distribution part of the grid. These are the analytical or offline applications, right, to do analyses in different areas like short circuit study, distribution power flow. You know, the distribution power flow is a full 3-phase unbalanced power flow for distribution, right? And then an ancillary or set of additional applications that are running on the ADMS, okay? So today, the goal of many utilities is to have a fully digitized grid. And to do that, we need to make sure the utility has a strong grid before we think about smart grid. Strong grid before smart grid. And by strong grid, we mean a communications infrastructure that can support all the applications, right? The response requirements in seconds, bandwidth requirements in bits per second, and latency requirements, you know, in seconds. And also the IT infrastructure. As I said, we need to do enterprise data management, and we need IT and OT working together, right? Operations and IT. So if a utility wants to have a digitized grid, no organization can do that in one step to go from where they are today to that goal. So we help them with a roadmap. So where is that organization today? They may be manual control. Could all of you please stay muted? Okay. Please mute yourself if you're not muted. Manual control and legacy methods. And then let's help them get to that goal, but in steps. So the second step may be remote control and monitoring, SCADA, adding trouble calls and smart meters and circuit reclosers. And the second step gives them 28% lower customer minutes interrupted than the base case. So it's a significant improvement and significant benefits. The next step would be automation and visualization, distribution automation, network visualization tools, outage management, prediction analysis. Now it's 43% lower customer minutes interrupted. Again, significant benefits. And then eventually digitally enabled grid, okay? So in the real world, you know, we help organizations put a roadmap together and then achieve each of the steps. Now here's a utility with 856 distribution circuits. That's a lot of circuits. And they want to improve their reliability. Well, it'd be very expensive to automate all 856 circuits. So we study the circuits and we find that only 23% of the circuits account for 71% of all the outage minutes. So if we automate just 200 circuits, or 23%, we address almost 3/4 of all the outage minutes, okay? Much wiser use of money than trying to automate all the circuits, okay? So my point here is we need to look at engineering many times from a business point of view. That's why after I got my bachelor's and master's degrees in electrical engineering in power, I got an MBA in finance. That helped me understand the business side of engineering. Okay, it gave me very strong financial tools to do that analysis. Okay, and I really think a good engineer needs to understand the business side of the technology too. Now, to get the maximum benefit from microprocessor-based devices, there's different types of two different types of data in a device. The operational data is what is sent up to the control center for the operators to use to monitor and control the power system. And these are points like current, voltage, real and reactive power, alarm information, things like that. Or there's non-operational data. These are points and files. And this is very valuable information, not for the operators, but someone other than the system operators. Could be the maintenance group, asset management, planning, engineering, other groups. And this could be like a digitized waveform in a relay, could be maintenance information, very valuable information. So we need to understand that there's different types of data. I introduced these concepts in 2003 in an article in IEEE Power and Energy magazine. That's the magazine for power and energy members, okay? And these are now industry standard concepts. Operation.
Hello. Rishika,
Yes, sir.
are you okay? But actually, we are not getting the voice of our honorable speaker. So I think he is facing connectivity issue. So he will join back within couple of minutes. Kindly wait.
Okay, sir.
Uh, Dear participants, due to some connectivity issue, our honorable speaker has left the meeting and is going to join shortly, hopefully. Kindly wait. Yes, just I have got a message from our honorable speaker. He is going to join shortly. He has left due to power outage, and he is in home right now. So just he has given me signal. He is going to join shortly. So we can wait, please. Yes, our honorable speaker has joined. Sir, welcome back in the meeting, sir, honorable John McDonald, sir.
Yeah, I'm not able to start my video.
Yes, uh,
Could you let me do that? There you go.
Yes,
Okay.
yes, now we
Sorry
are good.
about
Yes,
just
sir. Welcome back, sir.
had a power outage at my house. Um, let me go back to the file here. And sorry, I'm really sorry for that interruption.
No problem, sir. We are waiting eagerly and going to listen further.
I'll share my screen again. There we go. Can you see the screen?
Yes, sir.
Okay.
I can see.
Very sorry. I want to make sure we have some time for questions. So um, this is the Internet of Things. This is really exciting because this is the next productivity revolution that we're in the middle of now, with connecting intelligent machines with big data and analytics, and with people, connecting people any place, any way, any time for intelligent operations. And the connection is done through communications. So remember what I said was a strong grid before a smart grid. And part of the strong grid is communications infrastructure. You know, when I was an undergraduate electrical engineering student and I really wanted to specialize in power, I learned right away that I needed to learn a lot about communications, because communications is the enabling technology that allows us to automate, right? Communications is key to automation. So we really need to understand and learn a lot about communications. Um, and on the left side here is the typical situation in many organizations today. Each group is siloed. They have their own systems, their own IEDs. An IED is an IEEE term, which means Intelligent Electronic Device, microprocessor-based devices. So each group has its own systems, devices, and repositories or databases, but there's no sharing. And on the right here is what our goal is to break down those silos and bring all the groups together with a federated data mart, okay? Bringing everybody together. So all the data sources in the enterprise, we've identified all the valuable data and make sure that all the users, the operational data users and the non-operational data users, have the data that they need. The advantage then is on the left side, we have a standard architectures in the substation that we're showing here, a master data concentrator, slave data concentrators, and talking downstream and getting the operational, non-operational data from the intelligent electronic devices. To the right here, we're in cyan or light blue, we show all the data sources in the enterprise, and in green are all the users in the organization who now have all the data that they need. So this is really the journey to digital transformation. This is, if I was a student or young person today, I would print this out and put it up in my office, because this is really what's happening. You know, we started with reactive in the lower left, and today we're at predictive, where we're learning what health information do I need from the asset, and what analytics do I need to predict the failure modes. But with more artificial intelligence, more machine learning, and more use of the digital twin, we're eventually going to reach autonomous, which is self-healing, self-provisioning, and extensive autonomous operations with limited human intervention. Okay, and then I mentioned standards are important, and what I want to show here is these are the 16 foundational industry standards for smart grid. So even though there's hundreds of standards out there in industry, these 16 are the most important. So it makes it easy for you to figure out which ones are relevant to what you're doing. Remember, the landscape of smart grid is turbine to toaster, a power plant all the way to your home. That's generation, transmission, distribution, and your home. And these 16 standards cover that whole landscape, okay? And what's nice is today in the world, there's one standard for control center to control center communications. There's two standards for control center to field equipment, and really one standard for within the field, that's IEC 61850. So we've converged now globally on a very small number of standards that are accepted. And then lastly, the one thing that's important is when you're doing projects, at some point you should stop and look back. What have I learned and what changes will I make going forward? And this is what we did with implementing smart grid projects. And remember, a holistic solution is a set of components. And if you have a chain and you pull the chain very, very tight, the chain is only as strong as its weakest link, right? If you pull it and it breaks, there's one link that was weak that broke and the whole chain broke. So with a holistic solution, it's only as mature as its least mature component. So you really want to check the component technology. And we found initially that some of the component technology was not as mature as advertised, which made the whole solution not as mature, okay? So we would have to field re-engineer or upgrade certain components. But we anticipated that because the ultimate test of a holistic solution is putting it in the field. You can test it in the office or the laboratory for many, many years, but the real test is when it's in the field. Secondly, integration and interoperability. I said two key words, and standards are so important there, industry standards. Third is testing. You want to do as much testing as you can in the office or in the lab before you get to the field. Easier to fix things in the lab. What we really found out was that project management is key to the success of a project. You could have the best technology in the world, you could have the best engineering team at the customer, but if you have a weak project manager, the project could be unsuccessful. So we really found that project management was key, in addition to a strong engineering team and very good technology. And consistent project management guidelines are important, consistency across all the projects. And we said, with the customer, we want to build an A team of the very best project and technical members, both. And also, lastly, a new major stakeholder in any smart grid project is the end use customer, the residential commercial customer. For many years, we never engaged with customers, right? We didn't have to. Somebody would read a meter, a meter reader from the utility would read the meter, and a bill would be generated and the customer would pay the bill. There was no engagement with customers. But now when we put smart meters on customers' homes, customer engagement is critical. It's very important. And many utilities today have chief customer officers. There's many programs being put together for end use customers today. It's very, very key in the industry. And so we really have to learn a lot more about the end use customer. Okay. And that was, let me stop sharing. And that was the end of my talk. And I don't know how much time we have. Sorry for that interruption with my power outage. But if we have any time, I'd be happy to answer any questions or be interested in any comments.
We are on time, sir. We are on time. And
Okay.
any participant, if you have any question, because the maximum are undergraduate students, and smart grid is a very important topic of the research. So if you have any question related to smart grid, so you can ask.
Good evening, sir.
Hi.
Sir, I have a question. So, what are the suitable areas of research in smart grid, especially in microgrid?
Good question. Let me some of the needs we have with smart grid. Okay, one would be the application of power electronics. Like, remember I talked about bringing power, the applications of power electronics in power system monitoring and control. Okay, many of our controllers today are mechanical, and we really need to move to power electronic based controllers. And these are three examples in my article are online tap changers, low voltage network dynamic grid edge controllers. We're putting controllers now at the edge of the grid, and smart inverters. Okay, so that's one. Second would be the application of data science to power systems. We're hiring a lot of data scientists today because we want decisions now to be driven by data, a data-driven organization. So we hire data scientists, but the data scientists we hired are data scientists. They don't know anything about the power system. We have to teach them about the power system. So in research, if you have a good understanding of data science and domain knowledge of the power system, that's a unique combination that's in demand today. Okay, that's a second one. And I would say a third one would be to really understand the challenges of the integration of distributed generation with the electric grid. You can imagine customers, they want electricity all the time. How do you get electricity if you're using photovoltaic panels and wind turbine generators and the sun's not shining or the wind's not blowing? You still have to provide electricity to the customers. So, distributed generation is very nice from an environmental point of view, but when you're an electric utility, your job is to provide electricity to your customers. What do you do when the distributed generation isn't generating? How do you satisfy your customers? So there's a lot of challenges today in the integration of distributed generation with the electric grid. Okay, so those are just a couple. Does that help?
Yes, thank you. Thank you so much, sir, for giving the answer. And sir, we have two questions, and students has asked in the chat box. We can see. First question is asked by Ashutosh Verma. He is asking, what are the different stability issues in future smart grid? Sir, what are the different stability issues in future smart grid?
The biggest issue in the future smart grid is really the stability of the grid from the point of view that today we have a lot of large power plants, and in those power plants are large generators, right? Coal-fired, oil-fired generators. And the rotors, right, on those generators are very big, and they have a lot of inertia, okay? When there's a problem on the grid, this tremendous amount of inertia protects the grid and keeps it stable. You just can't slow down or stop this large inertia quickly, right? That inertia helps you keep the grid stable. Things can't happen, things cannot stop. Things can't happen or slow down quickly. There's a tremendous amount of mass and inertia, and that helps with stability. If your grid is 90% renewable or 100% renewable, you don't have that inertia anymore, right? You just have a lot of inverters. How do you keep the grid stable when there's a problem? And that is the biggest issue today is lack of inertia as the penetration of renewables grows, and grid stability. That is the one biggest issue today, is how do we do that? There's a lot of papers written on that and a lot of research on that that's available online. Okay.
Thank you so much, sir. And sir, actually, maximum are second year students, BTech second year student, and one BTech is second year, and it is the last question. And if any participant, we are going uh, exceeding the time, so we will share the email ID of honorable sir, so we can ask also. And the some videos are already up there, uploaded in the YouTube, so we can take help from the those videos also. Sir, our last question is, how much accurate are these smart systems are in early fault detection? Is this technology fully developed in power systems? One second year student, Anant Verma, is asking this question, and it is given in the chat box. How much accurate these smart systems are in early fault detection?
So the answer to the question is it's much more accurate today than it was 4 or 5 years ago. And the reason is that our protective relays today, we can model very accurately the location of that protective relay on the grid. We can model the grid in that protective relay. So when a fault occurs, the relay can detect the fault very quickly, but also it's able to locate the fault, okay, which is something we weren't able to do previously. Previously, the protection equipment wasn't able to locate the fault. We knew there was a fault, we knew which feeder it was on, but then a utility crew would have to go out many times at night, many times in a storm, like a monsoon or a lot of rain, and with lights would have to patrol the line and look for the problem, okay? Today, the protection equipment can not only detect the fault, but locate the fault to a small area of the feeder. And so it can automatically detect the fault, locate the fault, and isolate the fault, and restore service upstream and downstream of the faulted segment, all with no human involved. Okay, so a couple things. One is accuracy, and the second thing is self-healing, right? The ability to self-heal. Now, these accuracy with location of the fault is very good on transmission, very good on subtransmission, very good on the upper levels of distribution. But as we get to the lower levels of distribution, where you have a lot of laterals, right, and a lot of feeders and laterals, it becomes less accurate. Okay, so it really depends where on the grid you are with respect to accuracy. But it's the accuracy is very, very good, except when you get down into the lower levels of the distribution system, right?
Uh, thank you so much, honorable sir. And I think all questions have been answered by our honorable speaker. So I want to request from all the participants, after vote of thanks, kindly wait, because we will take a group photograph with open the video. So now, Rishika, it is over to you, please. Rishika, anchor.
We thank you, sir, for your stimulating presentation. Now, I would like to welcome the convener of this event, our advisor, Dr. Khadi Moin Siddiqui, sir, to deliver a vote of thanks on behalf of the entire IEEE SRMCEM student branch. So please.
Thank you so much, Rishika. Rishika, am I audible? Am I completely audible?
Yes, sir, you are audible.
Okay, thank you. Okay, thank you. So, a very good evening, everyone, especially Honorable Chief Guest, Sir John McDonald, a Smart Grid Business Development Leader, GE's Grid Solutions, past President, IEEE Power and Energy Society, IEEE Life Fellow, Honorable Guest of Honors, Professor Ashish Kumar Singh, immediate past chairman, IEEE UP section, MNIT Allahabad, esteemed director, SRMCM, Professor Dr. Bhavesh Kumar Chauhan, Dr. Indu Prabha Singh, branch counselor, HODs, faculty participants, student participants, and volunteers. It's my proud privilege to propose vote of thanks on the event inauguration ceremony of Power and Energy Society chapter SRMCM Lucknow. First of all, my sincere thanks and deep gratitude to Honorable Chief Guest, Sir John D. MacDonald, IEEE Life Fellow, a Smart Grid Business Development Leader, General Electric Grid Solutions, USA, who has accepted our invitation gladly and always ready to share his enormous knowledge on power and energy. Honorable Sir, your gracious presence has motivated us a lot, and always we take inspiration from you to do betterment for the humanity with the use of advanced technologies. Honorable Sir, your great experience and exemplary contribution for the humanity is highly appreciated. Again, thank you so much, sir, for giving us your precious time. Indeed, your expert lecture on the smart grid is opening the doors of new researches, and hopefully we and our students will do much better for the contribution of humanitarian via advanced technologies. Honorable Sir, no doubt we have learned a lot from your today's talk and will not hesitate to say that you are one of the most influencing and dedicated personality of the world in power and energy. Again, thank you so much, sir, for giving us precious time. Further, my profuse thanks and gratitude to Professor Ashish Kumar Singh, immediate past chair IEEE UP section, MNIT Allahabad, for your gracious presence in the program as guest of honor. Today, whatever our IEEE students branch is doing, it is due to your enormous motivation and guidance. From the beginning to till date, you are firmly stand with us and handholded because of your but because of our quality hard work and commitment in the right directions. Honorable sir, thank you so much for accepting our invitation and get ready to guide us again and again. I take this opportunity to express our sincere thanks and deep gratitude to Professor Dr. Bhavesh Kumar Chauhan, Honorable Director, SRMCM Lucknow, for his esteemed presence amongst us and for presiding over the event. Honorable Sir, without your productive mentorship, useful and critical guidance, we are unable to organize this kind of program successfully. Thank you so much, sir, for your untiring efforts and constructive guidance. Further, I would like to express my sincere thanks to respected branch counselor SRMCM Dr. Indu Prabha Singh for her time-to-time support. Now, thanks to all HODs, faculty participants, student participants, volunteers for joining us and making the event successful. At last, thanks IEEE SRMCM student branch members and newly formed PES executive committee members such as Mr. Ambar Mishra, Mr. Ashutosh Verma, Ms. Pratishta Singh, Mr. Ayush Pandey, Mr. Anant Verma, Ms. Rishika Pandey, Mr. Abhishek Singh, and Mr. Harshit Jaiswal for your hard work with great enthusiasm to conduct this program in the effective way. Again, thank you so much all. Now, Rishika, we will go for the Guru photograph. So kindly request to all the participants to open their video. So we can take a photograph with our honorable chief guest.
I request everyone to open their.
And Amber, take photograph, please.
Yes, sir. Yes, sir. The photograph is
Thank you so much. Thank you so much, Honorable John McDonald, sir. Actually, today was a weekend, and you have given us your precious time because we understand what your time, what your time is value. But you always, whenever we sent an email again and again, you just say, "Okay, just I'm coming," and it is our motivation because you see, you can see now we have a second BTech second year students in our executive committee, And you can see here when they are speaking in the starting, they had some hesitation because they are doing first time. But now we have listened your leadership lesson, and hopefully, and we will show in future we will produce some strong leaders, and they will serve for the humanity, and we will be witnessed. They will contribute in the at large in the society, nation, as well as world. So thank you so much, Honorable John McDonald, sir, and your inspiration, motivation, and guidance is always important for us, and our students are committed to do. Rishika,
Yes,
uh,
sir.
you speak to our honorable chief guest. You are committed to do for the betterment of humanity or not?
Yes, I'm looking forward to do some projects and learn everything that I could in this sessions and being a part of my critical member.
Yes, very good. And Ashutosh, you are very active volunteer. So what you would like to say? Because you are working from 1 year and you are mentoring to them.
It is very honor for us that Sir McDonald has given us such beautiful webinars, and I have also seen some previous webinars also for us. Sir, thank you, sir, for coming and giving a express talk on this smart grid. And I will surely looking forward also to give some webinars on our college again.
Yes. Actually, our honorable speaker, honorable chief guest, are always ready to give us whatever we are expecting, and he like to give more and more. So thank you so much. Pratishta is here. Pratishta.
Yeah, let me just say that I wish you the very best of success in your new chapter. Okay, but listen, don't feel like you have to do this all yourself. There's a lot of resources available. I mentioned many things that are online, that are available at no cost. Okay. Also, there's many people who would love to help you. I'm one. I if you need any help with leadership training, leadership experience, technical talks on different subjects, I could help you. I could also get other people that would be happy to help you too. Okay? So don't hesitate. Please reach out. Reach out to us. Ask us for help. We want to help you because we want you to be as successful as you can be, both as a chapter, but also as individuals, right? Each of you, there's no limit, right, to what you can do. Don't limit yourself. Take advantage of all these opportunities that are available to you and really advance your career. Okay, do the very best you can individually as well as for the chapter. All right? But again, don't hesitate to reach out and ask for help. There's many people that would love to help you. And I mean that, okay? We're always wanting to help you. So please take advantage of that. And again, thank you for the opportunity to be with you, and congratulations on the new chapter.
Thank you so much, sir. And you will see in the upcoming months we will organize some more programs for the benefits of our students. So thank you so much, honorable sir. Thank you so much for joining us. And now when our students will be ready and they will have some skills and knowledge, and if they will not have hesitation, then we will conduct your interview under our IEEE PES chapter, and our students will interact to you, and then at that time you might be inform me our students have got something else whatever they do not have right now, sir. Yes, sir. Thank you so much, honorable sir, for joining us. Thank you so much. Yes.
Thank you. Yeah, thank you again.
Thank you so much. So now, sir, with your permission, can we close the program officially? Yes, sir. Thank you. Thank you so much. So now all can leave the platform. Yes. Thank you so much to the participants. Thank you so
Thank
much.
you, sir.
Thank you so much, sir. Have a nice
Sir, bye bye.